lecture from chapter number 9. We will continue studying pseudo nMOS logic, and we'll study relationships for VOL, relationships of VOL for NAND2 and NAND3 gates, right? So a NAND2 pseudo nMOS circuit can be drawn like this. We have only one PMOS transistor, and we have two NMOS transistors in series. This means we studied in our last lecture that the resistance will be doubled because they are in series, but beta, which is inversely proportional to resistance, beta would be half. So the effective beta for NAND2 is beta n by 2. So this is beta of NAND 2. So the effective beta is half of the beta that we have in case of a NOT. Beta n that we have in case of a NOT divided by 2. Similarly, effective beta for NAND 3 is the beta that we have in case of NOT divided by 3. So to get VOL of NAND 2 is equal to the VOL of NOT, what should we do? We should have, for example, we have this NAND 2, and the resistance of the path is 2 times the resistance of this path as it was in case of a NOT. So how to make the resistance of this path equal to the resistance of this path that was in case of a NOT, right? We have to decrease the resistance of each transistor by 2. This means we have to double the beta. So if we double the beta, the resistance will be decreased to half for each transistor, and R by 2 plus R by 2, that would be R. So what we should do is we should double the beta that we used in case of a NOT if we want to have the same VOL for NAND 2 that we had in case of a NOT. Similarly, to get VOL of NAND 3 equal to the VOL of NOT, we have to make the resistance of this path equal to the resistance of the path that we had in case of NOT. So the resistance of the nMOS array can be set equal to the resistance of the nMOS array that was in case of NOT if we make each transistor 3 times as it was in case of NOT. So that is Rn by 3 plus Rn by 3 plus Rn by 3 makes them Rn. So if we want to equate VOL, we need to fabricate each nMOS transistor 3 times as it was in case of NOT. So it's pretty straightforward. Now we'll solve an example where we are given these parameters VDD, VTN, VTP, kappa n, kappa p, and aspect ratio of P is given. So what is required? VOL, we want to have VOL is equal to 4. So we want to have the beta n of each transistor if we want to implement a NAND 2 using these settings, and beta n of each transistor if we want to implement a NAND 3 and we want to keep VOL is equal to 4 volts in both these cases. So we want to implement a NAND 2 having VOL is equal to 4, a NAND 3 that also has a VOL is equal to 4 volts. Right. So we know that if we somehow compute VOL for NOT under these settings, it's easy for us to compute. If we somehow set beta n for NOT, beta n for NOT, beta n of NAND 2 is straightforward. We should multiply beta n of NOT by 2. And if we compute this same beta n of NOT, we'll multiply with that value by 3 and we'll get beta n of NAND 3. So to compute beta n for NAND and beta n NAND 2 and beta n for NAND 3, we must first know the basic item, that is beta n of naught. So if we know this beta n of naught, we can compute these two quantities easily by multiplying 2 and 3. So once again, we regress back to the same equation that we used in the first lecture of 9th chapter. This is in its active mode. PMOS transistor is in saturation mode. We put these values that are given: VDD5, VTP 0.85, VOL4, VTN 0.7, and we get beta n over beta p, this ratio equal to 6.92. Lastly, this ratio can also be written as, this beta n can also be written as kappa n aspect ratio of n, which we don't need. Just make it beta n because we have to compute beta n. So we don't need to write its equivalent here. Whereas we'll write the equivalent of beta p, which is kappa p times aspect ratio of p. So we are given aspect ratio. We are given the value of kappa p, which is 55. Aspect ratio of p is 2, and beta n is the only unknown here, which comes out to be 6.34, and this is for a naught. So the rest of the things is very simple. The rest of the things are very simple. Beta n for NAND 2 can be obtained by multiplying this value by 2, and for NAND 3 we can compute it by multiplying this value beta n for naught, multiplying it by 3. So we'll solve one more example using pseudo nMOS before we move ahead. Thank you.